We previously learned a lot about the structure and nature of waves. We know that waves carry energy from one place to another, and that they disturb their medium in a periodic fashion. Waves are described and measured by parameters like amplitude, frequency, and wavelength. We can see waves in water and hear waves as sound, but we haven't yet discussed the waves that we perceive as light. Visible light is only a small part of a group of waves we call electromagnetic waves. To learn more about light, we'll first have to understand the electromagnetic spectrum. The electromagnetic spectrum describes a wide range of different electromagnetic waves. Also called EM waves, these are a special type of wave that can travel without a medium. Unlike sound waves and water waves, electromagnetic waves don't need a fluid or a solid or even air to help them travel from one place to another. EM waves can travel across the great vacuum of space, which is why we see light from distant stars and planets. Electromagnetic waves are named for the fact that they have both an electric and a magnetic component. They begin when charged particles, like electrons, vibrate due to the various forces acting on them. The vibration of charged particles results in an emission of energy known as electromagnetic radiation. EM waves propagate outward from the source. Just like regular transverse waves, the oscillations of EM waves are perpendicular to the direction of the wave's travel. But EM waves are more complicated. The electric component oscillates in one plane, while the magnetic component oscillates in a different plane. In a vacuum, EM waves always travel at the same speed, the speed of light, which is roughly 300 million meters per second. We call this value the speed of light, but really it counts as the normal speed for all of the EM waves. So what are the other EM waves besides light? Electromagnetic waves include infrared, ultraviolet, radio waves, and microwaves. They also include X-rays and gamma rays. You've probably heard of all these waves before, but you may not have seen how they relate to visible light. Let's take a look at how these 7 groups of waves fit together on the electromagnetic spectrum. The EM spectrum is the range of all possible frequencies of electromagnetic waves. At one end of the spectrum are the waves with the lowest frequencies. At the other end are the highest frequency waves. The spectrum is broken up into regions that define each of the different wave types. At the lowest frequencies, we have radio waves. Then, as we increase frequency, we encounter the microwaves, infrared radiation, and visible light waves. Moving further up the spectrum, we have ultraviolet radiation, X-rays, and gamma rays. Gamma rays have the highest frequencies of all the EM waves. Electromagnetic waves can also be distinguished by their wavelength. Wavelengths for EM waves can be found by dividing the speed of light by the wave's frequency. This is a modification of the wave equation. Since all EM waves travel at the speed of light, then the spectrum of wavelengths is exactly opposite the spectrum of frequencies. In other words, wavelength and frequency are inversely proportional to each other. We can view our electromagnetic spectrum not only in terms of increasing frequencies, but also in terms of decreasing wavelengths. As frequencies increase on the EM spectrum, wavelengths decrease. So that means radio waves have the largest wavelength and gamma rays have the smallest. To help you associate these relationships across the spectrum, try to imagine a continuous wave with gradual changes throughout. The wave begins with very wide arcs, indicating the large wavelengths and low frequencies of radio waves. As the wave moves along the spectrum, the crests and troughs get closer together. By the end, the arcs are so close together you can barely see between them. This represents the high frequencies and small wavelengths of our gamma rays at the end of the spectrum. Electromagnetic waves are tough things to imagine. I mean, it's not like we can actually see or feel them as we can water and sound waves. Where does electromagnetic radiation come from? We already said it originates from the vibration of charged particles, but what does that really mean? What are the sources of those charged particles? Radiation in the visible light range comes mostly from the sun. Light bulbs, burning flames, and certain animals can also be sources of visible light. Infrared radiates from the sun and other warm things like people, electrical appliances, and distant galaxies. Most microwaves that we know about come from devices that we have invented to generate them, but there are microwaves coming from the sun and from the universe in general. Stars and lightning are natural sources of radio waves, but these are also produced by the antenna on a radio transmitter. On the other side of the spectrum, we have ultraviolet radiation, which is emitted by black lights and fluorescent lamps. Of course, the main source of UV rays is the sun, which is also a major source of X-rays. Both X-rays and gamma rays can be made by machines used in diagnostic imaging, but gamma rays come naturally from the decay of radioisotopes. You can see that in general, all of the electromagnetic waves are emitted from objects in space, and all of them can be produced by our technology. At the end of the day, though, the narrow band of visible light remains the only region of the spectrum that we can actually see. EM waves originate from the vibration of charged particles, and unlike other waves, they can travel without a medium. The vast range of frequencies for EM waves is described by the electromagnetic spectrum. The spectrum stretches from the lowest frequency radio waves to the highest frequency gamma rays. We can also describe the EM spectrum in terms of relative wavelengths. The size of the wavelength decreases continuously from radio waves to gamma rays. Different wave types originate from different sources, but most of them are emitted from objects found in outer space. Humans have developed a wide range of technology to produce electromagnetic waves. These machines are used in medicine, communication, and general convenience.